Hello everyone, welcome to my channel. Today we are going to solve a very interesting problem. This problem is on functions equation. Here functions equation is given as fx equal to 1 over t 0 to t f of x plus y minus fy dy. Here also function is a differentiable function and its domain is set of real numbers and its range is also set of real numbers. We have to show that there exists a constant c such that fx equal to cx. Function also a linear function. We have to show it. This is the problem. Now let's start. Here function's equation is given as fx equal to 1 over t 0 to t f of x plus y minus f of y dy. You can see that the function is integrable because the function is differentiable. Function is differentiable, so it is integrable. And this integrable function has also its antiderivative. Always integrable function has always its antiderivative. There exists antiderivative of any integrable function. Now suppose we consider antiderivative of the function fx as phi x. So integration fx dx equal to phi x plus c. Phi x is considered as the antiderivative of the function fx. So we can write integration fx dx equal to phi x dx. Every integrable function has its antiderivative. So also we can write phi dot x, that is derivative of phi x equal to fx. Derivative of phi x equal to fx. Now the function equation is given as this. So the function equation is given as 1 over t 0 to t f of x plus y minus fy dy. We have got phi dot x equal to fx. So we can get f of x plus y equal to phi dot x plus y, and f of y also equal to phi dot y. This is so this function equation is 1 over t 0 to t f of x plus y minus fy dy. We can put those relations in this function's equation. 0 to t f of x plus y equal to phi dot x plus y. So we can put these values of f of x plus y, whose value is phi dot x plus y, minus fy is phi dot y, Here derivative is also taken as with respect to y. This derivative differentiation with respect to y, variable y. So we can write 1 over t 0 to t 0 to t phi dot x plus y. Here integration with respect to y, so its derivative is taken as differentiation with respect to y. So we can write phi dot x plus y is d dy of phi of x plus y minus d dy of phi of y. This is dy. So this is equal to fx equal to, so fx equal to 1 over t 0 to t dy phi of x plus y dy minus 1 over t 0 to t dy phi y dy. So it is also equal to 1 over t 0 to t dy dy of dy, which is written as d, which can be written as d phi x plus y minus 1 over t d phi y 0 to t. This is, so we have got fx equal to, so fx equal to 1 over t d of phi xy is only phi xy, because integration dx is x. So this integration is phi x plus y 0 to t minus phi y. This is also phi y, integration of d phi y integration is phi y, and its limit are 0 and t. Upper limit is t, lower limit is 0. We can put these two limits on these two functions. We get 1 over t phi of x plus y, x plus value of y is t minus value of y 0, when 0, then this is phi of x plus 0. Lower limit of y is 0, lower limit of upper limit of y is t. So this is, because the integration was with respect to y, integration was with respect to y, so the ranges are the ranges of y, or that is upper limit t, y is t, and lower limit of y is 0. We can put these two limits of y minus 1 over t phi of t minus phi of 0, 1 over t phi of x plus t minus phi of x minus 1 over t phi of t minus phi of 0. We have got this result. Now phi of x is differentiable for all x to the set of real numbers. For all x belongs to set of real numbers, phi x is differentiable because we have taken phi x as the antiderivative of the function f(x). That is, we have taken because we have taken phi dot x equal to fx. So phi x is differentiable. Phi x is differentiable for all x belongs to the set of real number, that is entire domain, on entire domain. As phi x is differentiable, so it is also continuous there. So phi x is continuous there. Phi x is also continuous there because any differentiable function is always continuous in that domain. Differentiable, any function is differentiable in certain domain, the function is also continuous in that domain. So here phi x is continuous. Now we can apply, we have the opportunity to apply the mean value theorem, that is Lagrange mean value theorem, on these two expressions. First expression is phi x plus 2 minus phi x, and second expression is phi t minus phi 0. Here two interval can be considered. First interval is x plus 2, open interval is x plus 2, and also closed interval x plus t, and here open interval 0t and closed interval 0t, where phi x is differentiable for all x belongs to R. If we take two interval, if we take two intervals closed or open, closed interval x plus t and 0 t, then we can apply psi x, psi x is continuous in x plus t, psi dot x exists in x plus t, because psi dot x equal to f, that is psi x is differentiable for all x belongs to R, and these two intervals are taken from the entire domain R. That is, these two sub interval are the subsets of the entire domain set of real numbers. Now the phi dot x exists in x plus t, and also phi t is continuous in 0t, and phi dot t exists in open interval 0t. Here t belongs to the set of real numbers. T also belongs to the set of real numbers. T is greater than 0. It is also a real number. So phi dot exists in this in open interval 0t. So we can apply Lagrange mean value theorem. So we can apply Lagrange mean value theorem on both functions phi x and phi t. So we can apply we have the opportunity to apply Lagrange mean value theorem on both these functions. Functions are phi x and phi t. Phi x and phi t. So we can apply Lagrange mean value theorem on both phi x and phi t. So phi of x plus t minus phi of x equal to Lagrange mean value theorem states that if a function fx is continuous in any closed interval ab and its derivative exists in open interval ab, then there exists a point xi such that phi of b minus phi of a equal to length of the interval into phi dot xi, where xi is an intermediate point in this interval. So here we can write the length of interval is x plus t minus x into phi dot xi, here xi lies between belongs to the open interval x plus t, lies between x and x plus t. Also xi can be assumed as xi equal to x plus theta t, where theta less than 1 greater than 0, theta less than greater than 0 less than 1. So x plus theta t is a point which lies between x and x plus t, that is belongs to the open set open interval x plus t. So phi of x plus t minus phi of x equal to t into phi dot x plus theta t. Also phi t minus phi 0 we can get from this relation if we put x equal to 0. If we put x equal to 0, if x equal to 0, phi of t minus phi of 0 equal to t phi dot theta t. Here this is got, and also we can apply the Lagrange mean value theorem on phi t, where there phi t's interval is taken as 0 t. So we can apply also mean value theorem on phi t, and we get this same result, that is phi t minus phi 0 equal to t phi dot theta t. Here also we put both sides x equal to 0, and after putting x equal to 0 on both sides we have got this expression, that these relations which can be got by applying mean value theorem on phi t also. This is the result. So phi t minus phi 0 equal to t phi dot theta t. Now we go to the initial step. Here initial step was fx equal to 1 over t phi of x plus y 0 to t minus 1 over t phi y 0 to t. This is also equal to 1 over t phi of x plus t, value of y upper limit and lower limit is 0, so phi of x plus 0, that is x, minus 1 over t, phi of y, upper limit of y is t, so phi t minus phi of 0. This is. Now we can put this value of these two expressions. First expression is phi x plus 2 minus phi x equal to t phi dot x plus theta t. So we can put the value of this expression, which is got as this value, t phi dot x plus theta t, t phi dot x plus theta t minus 1 over t. We have also got the value of this expression. The value of this expression is t phi dot theta t, t phi dot theta t. So this is equal to phi dot x plus theta t minus phi dot theta t. Here also we have chosen phi x as the antiderivative of fx. So we have assumed phi x as the antiderivative of fx. So phi dot x equal to fx. Phi dot x equal to fx. So phi dot x plus theta t equal to f of x plus theta t. Phi dot theta t equal to f of theta t. We can put these relations in this expression. We get phi dot x plus theta t equal to f of x plus theta t minus phi dot theta t equal to f of theta t. So when we put x equal to 0 on both sides, we get theta t equal to 0 on both sides. If we put theta t equal to 0 on both sides, we get f of x equal to f of x plus 0 minus f of 0. This implies fx is cancelled out, so f0 equal to 0. Now fx can also write f of x plus theta t minus f of x equal to f of theta t. If we divide on both sides by theta t, we get f of x plus theta t minus fx by theta t equal to f of theta t minus 0. We can write this by theta t. F of x plus theta t minus f of x over theta t equal to f of theta t minus 0 equal to f0. Value of f0 is 0, so we can put as 0 as f0. So this is f0 theta t. Now we can take limit on both sides. We can take limit both sides. Theta t tends to 0. Limit theta t tends to 0. Limit, we have taken both sides, limit theta t tends to 0. So this is limit theta t tends to 0, f of x plus theta t minus f of x over theta t equal to limit theta t tends to 0 f of theta t minus f of 0 over theta t. This is, and we are given fx as differentiable function. We are given fx as differentiable function. Fx is a differentiable function, so its derivative exists, and also this expression is the definition of the differentiation of function fx. This is the definition of derivative of the function fx. As a derivative of fx exists, that is, a function is differentiable, so this derivative exists, because function is given as differentiable function. So, and also this is the definition of the derivative of the function. So we can write f dot x instead of this. So f dot x is the derivative of the function. So f dot x equal to f dot, and this is also definition of derivative at x equal to 0. This is the definition of the derivative at x. This is the definition of the derivative, a particular value of the derivative at x equal to 0. This is the particular value of the derivative at x equal to 0, that is derivative at x equal to 0. So this can be written as f dot 0. This can be written as f dot 0, and also f dot 0 is a constant. F dot x exists in the domain set of real numbers, so f dot 0 also exists in the set of real numbers, and also f dot 0 is a constant, that is a real number. C a constant. F dot 0 is the particular value of the derivative of the function fx at x equal to 0. So this can be treated as a constant, and this constant exists in this domain, that is set of real number. There exists a constant c such that f dot x equal to c. F dot x equal to c. That is, derivative is constant. Function's derivative is constant. Function's derivative is constant, and also this constant exists in the set of real numbers, that is, c is a real number. So f dot x is also derivative of f x, so we can also write it as d dx of fx equal to c. D of fx equal to c dx. If we integrate, we get d of fx equal to integration c dx plus integration constant d. D is treated as integration constant. If we integrate this, we get f of fx equal to cx. C is constant, cx. Cx, integration of dx is x, c into x plus d. If x equal to 0, then f of 0 equal to c into 0 plus d. This implies also f0 is 0, so 0 equal to d. This implies d equal to 0. So fx equal to cx for all x belongs to R. So we have determined the function fx, which is a linear function, and its this expression is cx. The function's expression is cx. Function is equal to cx, and also c exists in the set of real numbers, and we have got function as fx equal to cx. Thus we have determined the function fx, which is cx. Fx equal to